Hello and good day to you. So what you've got in front of you is a set of visualizations for inside of a neural network. Top layer is the output layer, and as you can sort of see, there's 6 values that it's representing as the bars, which then split into 6 neurons that are below it, which each have 12 bars in that represent the 12 input neurons at the below that, and then there's 13 inputs, which are the flashing green and red at the bottom. And this neural network's insides are the result of a lot of attempts to try and figure out where the vanishing gradient problem is. In neural networks, there's a big problem in that you take the error in backwards propagation at the output, and you feed back that error down layers upon layers, and you get I think this visualization is a really good way of demonstrating why that might be a problem. Now, if you think about, even in layman's terms, that that error has to be weighted in that first layer, not only by not just by dividing it by 6 because there's 6 weights in that one neuron, but also relative to the input of those weights to the actual error. And then that's then recursively done to the next layer. So the next layer has 6 neurons with 12. So just imagine 6 times 12. You've already got a reduced error because you've already apportioned some of your error to the weights in the first layer. You then go down another layer to the what is the input layer, and that has 12 neurons with 13 weights each, and so 12 times 13, and again some of the error has already been calculated and apportioned to the mid layer. So there's even less of that error to apportion out. So sometimes with neural networks, what you end up is you get to your input layers and there's nothing left. Essentially, this is me trying to make it as simple as possible for you. There's essentially nothing left in terms of error to dish out to the input layers, and yet the strength of neural networks is that layering of different of the different neurons, which can then act as the logic gates. I mean, if you're not going to do it like this, if you're only going to have a couple of inputs and outputs, and you're not going to have any middle layer, you might as well just do regression and just go straight to linear or logistic regression, as the case may be. So this was a complete experiment for me. It's meant to be trying to speed up the learning and boost the learning in the bottom layer. If you notice, that layer's behaved a bit weird, if you have any understanding of how how this moves down, it should take a lot longer for those changes to happen. And I don't know whether this is actually accurate or whether I've just broken it. It just, a bunch of different experiments of trying to figure out a way of boosting the feedback further down the layers of the neural network. This seemed to be one way of doing it. So I'm going to quickly do a slide deck to talk about what I just said. We'll go back to the beginning. So the problem here is the vanishing gradient. So this is what we call the problem of apportioning out the error backwards and down the line in the neural network. They also talk about the exploding gradient, where it just gets really saturated at a really high output, which also happens. So AIs can they have a problem of being too explosive or too low sometimes, and they don't sort of work out the right output. So deep neural combinational networks are powerful, but with more layers and more neurons comes more splitting up of the error in your calculations, so you get ever smaller numbers. Now, something to learn from C++ is your doubles and floats. So you can go into a bigger memory than this, but if you think a double has 15.95 digits and a float has 7.22, and you probably get the gist that actually, when with the way the computer handles memory, when you go too small, it just drops off the ability for it to calculate. There's a bit of a chaos theory problem. So if you wanted to make a really, really big neural network, one way of doing it would be to add more and more memory for every single number it calculates. So it calculates every single number in its neural network to ever smaller floating point levels, and that's one solution. The other solution is trying to figure out a way of handling the way it does the maths so that you can boost the way it calculates these errors. And I don't think anybody's solved that yet. And this is more of a video just to say, if you're talking about AI, here's a presentation, here's something you should really think about, because there are limits. And this is the big thing that really stops me in my tracks and thinks the people who are saying AI is going to take over the world and take over their jobs are a little bit nuts, because they clearly don't understand the memory problem, or they clearly don't understand this vanishing gradient and exploding gradient problem. That actually the current neural networks we have are very much limited in the size and scale that we can put them at because of the way we calculate floats. I'm sure somebody will work out a better way in the future, but it's something that struck me, because I was doing the silly thing of assuming that in these arrays, these numpy arrays, they're all doubles, and it turns out the random function in numpy produces floats which are half the size. So I learned this to my shock when I was actually looking at the inside of this neural network and looking at the updates that it was doing to each of its layer in terms of the chain rule, and was getting to the bottom and seeing a bunch of zeros. So hence this video, to try and explain vanishing gradient and to set it up in your mind if you're watching out of curiosity. There's a problem there that somebody mathematically or engineeringly minded needs to solve. Anyway, thanks, have a good day.